It's a deep question and a subtle one, and there's sort of two ways that I like to think about that question. One is it could be that the Big Bang was an interesting event, but not the first event in the totality of reality. It could have been the first event that sparked the expansion of our part of space, but it could be that there's a grander realm of space within which we sit as a small part, and that grander realm may have been there for a far longer period of time. It may have experienced its own Big Bangs, maybe a collection of Big Bangs that may extend infinitely far into the past. So it could be that the answer to the question of what happened before the Big Bang is a lot of other Big Bangs or a lot of other quantum events that were taking place in a larger landscape of reality than we have direct access to. However, another answer is that the very question may not make as much sense as the words seem to suggest. We know how to parse that sentence. We know what it means to talk about the moment before the Big Bang because we know how to talk about the moment before your birth or the moment before the Civil War or the moment before any event that happened in the world. We fully understand the meaning of that kind of sentence. But it could be that when it comes to the Big Bang, the sentence actually doesn't mean anything. It could be that the Big Bang was the place where time itself started. And Hawking himself had a wonderful analogy to get this across. He said, look, I'll dress it up a little bit. Imagine you're walking on planet Earth and you pass by someone. You say, hey, can you point me in the direction of north? I want to walk in the northward direction. They point you, continue to walk. You pass by somebody else, say, hey, which way is further north? And they point you in that direction. But when you get to the North Pole and talk to somebody there and say, hey, how do I go further north? They look at you and say, whoa, that question doesn't mean anything because this is where north begins. There's no notion of going further north than the North Pole. And it could be that that spatial metaphor applies to time. Talk about 1 billion years ago or 10 billion years ago, but if you go to 13.8 billion years ago, the Big Bang, that may be where time started. And you can't go further back in time than the very origin of time itself.
Nothing was around before the Big Bang. According to Einstein's general theory of relativity, space and time together form a space-time continuum or manifold which is not flat, but curved by the matter and energy in it. I adopt the Euclidean approach to quantum gravity to describe the beginning of the universe. In this, ordinary real time is replaced by imaginary time, which behaves like a fourth direction of space. In the Euclidean approach, the history of the universe in imaginary time is a four-dimensional curved surface, like the surface of the Earth, but with two more dimensions. Jim Hartle and I proposed the no-boundary condition. The boundary condition of the universe is that it has no boundary. In order terms, the Euclidean space-time is a closed surface without edge, like the surface of the Earth. One can regard imaginary and real time as beginning at the South Pole, which is a smooth point of space-time where the normal laws of physics hold. There is nothing south of the South Pole, so there was nothing around before the Big Bang.
I know every scientist understands that we cannot see the entire universe right now. And that's because there's such a thing that we quantify as the observable universe. The universe has existed, we think, since the Big Bang, about, say, 13.8 billion years. So as you look farther and farther out into space, you necessarily have to look back in time. If something is 1 million light years away from you, like the Andromeda galaxy is about 2 million light years away, the light that you see through binoculars tonight as you look up at the Andromeda galaxy left 2 million years ago. We now have instruments that see so far. We can actually look back to about 400,000 years after the Big Bang. We can see so far out into space that the light has taken that long to get to us. The whole idea of the Big Bang has been given, I think, a real disservice. There are so many misconceptions. And certainly one of the biggest misconceptions is that people think that scientists feel that the Big Bang came out of nothing. Right? I mean, how did all of this energy and all of this matter that made up the universe, you're saying it just came out of nothing? No. I don't think any scientist actually believes that. The problem is, when you think about the condition the universe was in at that point, where, take our observable universe, right? You can look from one side of the universe to the other, back 13.5 billion light years or more. All of the stuff that we see was actually compressed into a space smaller than an atom, a volume smaller than an atom. We don't have the physics that describes how that would work. That is so much mass, so much energy in so little volume. At this point, there wasn't even mass, just basically pure energy. That right now, our physics doesn't go there. As we get a better idea about how gravity works under very extreme circumstances, huge energy densities, we may have some idea what set off the Big Bang, and possibly what came before the Big Bang. So today we actually have telescopes that are so powerful, they can see back to a time about 400,000 years after the Big Bang. That's amazing. We can see so far away in space that the light has taken that long to get to us, nearly 13.8 billion years. And when we look back to that time, the universe looks very different. For one thing, it's very hot. It's actually about as hot as the surface of the sun. And it's so dense and hot that we actually can't see any farther. Literally, in any direction you look around the sky, anywhere you look, if you look to that distance, you see the universe as it was at that time, 400,000 years after the Big Bang, and everything becomes just hot hydrogen gas. That's incredible. But what that means is that there's a limit, there's a bubble around us that we can see just because there's been time for light to come to us from those areas. Think about my arm being the universe before the Big Bang, in some kind of state that we can't even describe through modern physics. The entire observable universe that we can see now used to be a tiny volume of it, maybe an atom in my arm. One atom expanded and became the entire observable universe that we see. But that's not the whole universe. There are trillions of atoms in my arm. Each one of those could have expanded to actually be its own entirely observable universe. So we can't tell yet how big the universe was before the Big Bang, or even what shape the universe is, because all we're seeing is a tiny little bit of it that expanded to become everything that we see. That's not the whole universe. That's our observable universe. There's far more out there than what we can see.
In fact, this so-called inflationary cosmology is the technical name for the subject, says that. It says that it's quite likely that this explosive inflation of the region that we currently inhabit, it was just one of many such events. And therefore, there are other far-flung regions throughout this larger cosmological landscape where things have also inflated, but the details can be different. The physical details can differ from what we are familiar with. And the differences can be small, temperature differences in one part of space versus another, or they can be far more significant. Even the particles that make up that other realm may be different from the particles that make up our realm. Their masses can be different, their charges can be different, their fundamental physical features can be different.